I'm recording
Okay,
now
should
as well.
should I continue or wait a second then?
You can continue for now. Yeah, thanks.
Okay. I'll continue then. So as I was saying, there's this context where you're working in a company and a client comes to you asking, okay, this is my network, please optimize it. And they wanted it to be optimized with regards to, say, connectivity. So in a sense, they want to delete all of the not necessary or unnecessary edges and still remain connected. So this is obviously quite an easy problem. You might directly think we can just compute a spanning tree and send that to the client. And so that's what they did, more or less. I'm very much simplifying at the moment, but that's more or less what they did. They sent it to the client, and the client came back and said, well, no, that doesn't work because this is actually a train network, and this vertex here in the middle is actually Paris, and this is the train network of France, and we want to optimize that, and we don't want all trains to pass through one way to Paris. So the client didn't specify all the optimization criteria at first, and so they redid it. Maybe now it's a more central picture with Paris in the middle, but then the client had some other issues. For example, this vertex, which corresponds to Toulouse, now has to go all the way up to Paris to go back down to Marseille, whereas before it could go more or less directly. So this is basically saying that when you work with a client as a company, you might want to output a lot of possible solutions such that it might fit one of the or most of the criteria which the client didn't actually think of mentioning to you at first. And so this is where the enumeration is motivated from. This is one of the motivations. There's also some DNA applications for which it is very interesting, but I like this one. It's a nice story. So so enumeration is basically the art of efficiently, if possible, enumerating all feasible substructures. For example, spanning trees in a graph. And some kind of typical results and corresponding complexity classes are as follows. So one complexity class, which is usually regarded as quite efficient and quite a positive result, is polynomial delay. So this is to be understood as input polynomial, so polynomial with regards to the size of the input, whereas afterwards we'll see other kinds of polynomials. And so this class tells you that you are ensured to not wait too long between two feasible substructures. And so in practice, this is usually quite nice in the sense that if you have a solution, then you can send it to the client, and usually they need polynomial time to even verify it. So even if you can do better than polynomial delay, it's not always very interesting. On the other end of the spectra of complexity classes for enumeration, we have this very negative result, which says that no output polynomial time exists unless p equals np. So this condition is basically non-existent in the sense that, I mean, it's very likely that this basically means that there's no output polynomial time algorithm. And so here you can see the difference between when we state polynomial and input polynomial and output polynomial. So this output polynomial means that even if you consider having a lot of feasible substructures that you have to output, you cannot, I mean, if you have this result, then it basically means that there's no polynomial with regards to the size of that output that exists. So no algorithm that exists in that time, which is very bad in most cases. If you encounter such a result for a practical problem, you can basically try to change your problem. And then you have another result, which is somewhere in between. It's somewhat of a gray area. So you show that your problem is basically identical to a famous, or at least as hard as a famously unsolved problem in enumeration. And this problem is called hypergraph dualization. But I prefer to see it as enumerating hitting sets because they're basically the same problem, just presented differently. And so, yes, so this is basically a little context and preliminaries on enumeration. And what we thought of was putting some temporal graphs in there because obviously there's a lot of real-world applications where temporal graphs can be used. And for example, this train network, the client might come back to you and say, we don't want to change the train schedules. If this train only runs in the morning and this other train only runs in the evening, then there's no way for people from Paris to get over here. So we want to keep that into account as well. And so that's where this notion of, instead of spanning trees, you might want to consider this notion of temporal spanning trees or temporal spanners. So let's talk about temporal graphs and temporal spanners now. So my preferred model of temporal graphs is the following. You have some graph, which we often call G, temporal graph G as well. The non-temporal graph, we often refer to it as a footprint or an underlying graph. And in this underlying graph, we put some labels or times on the edges, which represent the appearance of the edge. So for example, the 0, 1, and 2 here means that this edge is present at times 0, 1, and 2, but not at time 3, whereas this edge is. And so we say that the largest integer that is used for these appearance times is called tau and the lifetime. Another way to represent it, which I have seen in this seminar already, is to just have multiple sort of static non-temporal graphs which follow each other in time. And so these are the same temporal graphs, just represented differently. And in these temporal graphs, you can now define a temporal sort of version of a path in graph theory, which is simply called a temporal path. Sometimes you might see it as being called a journey. And so this is basically a path in the temporal graph, such that all the times on successive edges are increasing from the last time. So to give you an example, this would be a temporal path going from this vertex to the middle, and then after moving to the bottom right, and then for some reason not doing anything in time step 2, and then ultimately going up to its destination at time 3. So note that we say strictly increasing here. So sometimes you might find it interesting to have non-decreasing. So for example, allowing 0 and then 0 and then another 0. In this paper, we don't consider, or at least in this presentation, we don't consider this model. We only consider the strictly increasing one. And it seems to fit well with the example of the train network from before. So now we have temporal graphs, temporal paths, and we can now define the concept of a spanning tree or a spanner in temporal graphs. We call a minimal temporal spanner a minimal size subset of timed edges such that some sort of connectivity is maintained. And this connectivity is defined through temporal paths. So I put this quote marks around connectivity because we're going to define in the next slide a few forms of connectivity. And so in the rest of the talk, most of the time when I say temporal spanner, I will mean a minimal temporal spanner. I will most of the time just drop the minimal. When I need to specify, then I will use non-minimal and minimal, but I don't think that it will happen. So let's now go over the temporal connectivities that we consider. So the first one is quite simple. We call it one-to-all, and it's basically what it says. Given a special vertex S can reach every other vertex. And so if you plug that into the definition of a spanner before, you can have a little example like below, where the graph are all the edges, and then a corresponding one-to-all spanner would be the black edges, whereas the gray edges are sort of deleted from the original graph. And you can see that S can reach everyone through only these 4 edges. Here's another one, a different one. Since we're interested in enumerating at some point, I was thinking I might show some different ones. So again, S can just reach everyone. The next type of connectivity we refer to as one-to-all to one. So it's basically one-to-all, but on top of that, your vertices, all the other vertices have to be able to reach S as well. So in the first example of a one-to-all spanner, that we gave, it actually corresponded to a one-to-all to one spanner as well, because all these other vertices can reach S as well. And this is another example of a one-to-all to one spanner. And note that this is not the underlying structure of this spanner is not a tree anymore, even though I claim it is minimal. So S can still reach everyone by going 1, 2, and on the other side 2, 3, and all the other vertices can reach S by going 2, 3, 4, and the last one can just reach directly. A third one, the second to last one that we consider is many to all. So this is extending the one to all concept to multiple special vertices or multiple sources. So in our example, we have S1 here and S2 here. And the spanner from before happens to also be a many-to-all spanner for these two sources. In other words, they can reach everyone through these edges. And this is another one, again, S1 here, S2 here, and they can reach everyone. And this one is has a tree structure. And lastly, there's the all-to-all spanners. So this is mainly what you might expect to read about whenever you read about spanners and temporal spanners. But in my line of research, it's always nice to consider simpler cases and then see how they transform or adapt to the more complicated or more studied cases. So I had to insert the above edge here because it turns out that the graph that I've been working on since this slide wasn't actually temporally connected. This guy could not reach this guy, so I had to add an edge. So this is, again, an example of an all-to-all spanner, and this is another one. And I claim that these are all minimal.
So just to clarify, so
Yeah.
in your formulation, only the ordering of edges matter. The actual duration happens between events doesn't matter.
As in the waiting time between arriving and departing? No, that doesn't matter in this presentation, at least. There are works that are interested in no waiting time paths, etc. But this is not of interest in this presentation, no.
I see. Okay.
Okay, thank you. So moving on, we have our temporal connectivities. We had our definition of a spanner earlier, and so now we're ready, and we had our introduction to enumeration. Now we put all of these together in the main sort of multi-problem that we study here, which we call temporal spanner enumeration. And so, which is the problem of when given a temporal graph G and a temporal connectivity among these ones, we would like to enumerate all minimal temporal spanners. And so below we have a little summary of our results. So you can ignore the extension column and the connected extension column. We will see what this is about in the next slide. But on the right, you can see that we have sort of these increasingly hard results, or from positive to negative, in a sense, results, starting with polynomial delay for 1 to all. So here m is the number of edges of a graph, and tau was the lifetime of the temporal graph. Then we obtain dual hardness for these two other ones. And then finally, for the all-to-all version, we obtain this very negative result, which I talked about before. So let's see how we obtain these results. So we start with 1 to all. And I need to talk to you about a very useful technique in enumeration first. So this is called binary partition. And the idea is very simple, very naive, actually. You start with an empty partial solution, and then you build a solution piece by piece. So it's a binary partition, which means that every time you have two choices, either you add an edge, say edge E1, to your partial spanner, or you remove it from the graph. And then you repeat with another edge, E2, and then you continue with E3, etc., until you've gone over all the edges of the graph. And then at the bottom of this binary partition tree, you have sort of solutions, or in our case, spanners. So this is what we would like to do, because you can actually, so maybe I should present it first like this. So if you only do this, then you might run the risk of having a very bad algorithm, because the number of solutions might be very small with regards to the number of leaves that you end up with. So the number of leaves is going to be exponential with regards to the number of edges, whereas the number of solutions might not be exponential with regards to that. So in that case, you might not even have an output polynomial algorithm. So that's very bad, but we can easily solve that by using this technique called flashlighting or extension. And so what we do is every step that we take in this partition tree, we check to see if when we add E2, can we still obtain a solution further down this branch? And if that's the case, then okay, very well, let's continue down this branch. And if it's continue down this branch here. And if it's not the case, then you can just ignore that branch because it's not going to be useful anyway. It's not going to give you a solution. So this all sounds very well, but how do you do this? You need to somehow check that there is a solution somewhere. So we do this, in our case, we call it the extension problem. So I give you a partial solution, which here is denoted by these bold edges, the thick edges. And we ask, can it be extended to a spanner with the remaining edges in our graph? And so this problem, we call it spanner extension. We show that this is NP-complete for the connectivity one-to-all. And we show this by a reduction from SAT. So here in SAT, you have the clauses at the bottom, and you have the corresponding literals or variables in the middle. And then the reduction that we do is we put S here, and then we basically tell it to make a choice between selecting the positive literal or the negative literal. Because if it chooses the edge that goes to the positive one, then it cannot choose the other edge, because otherwise the solution would not be minimal, as in 2 would not be necessary. But that's a contradiction because 2 is forced. It's already part of the partial solution. So that's the little technique that we use. So we show that this is NP-complete, which is bad, because that means we cannot use this as a little check for our flashlight algorithm. But one little thing with regards to this partition tree is that we didn't talk about the order of edges. These are just any arbitrary order, E1, E2, E3. Whereas if we now want the solution to be extended in a way that it remains connected, then we have this new sort of extension problem, which is called connected extension. And in this case, we actually show that it's in P, so that it's tractable. And this basically what it does, what we've shown is that you can sort of contract your partial solution into somewhat of a super vertex and then check if it can still reach everyone, which is efficiently doable. So what we then do is just plug that into the binary partition, and that's how, when we analyze the structure, obtain our polynomial delay. So we're happy with that. That's a good result. Next, we consider the one-to-all-to-one connectivity. And what we did at first was studying the connected extension again, because that worked for the last connectivity. It might work here as well. But even in this specific case of connected extension, we show that it's NP-complete. And we actually use the same structure as before, in which we just add these little paths that go back to S for every vertex. So I didn't add it for every vertex here, just for the leftmost one. But these little paths, 3, 4, 5, they're added everywhere. And we consider that these are part of the partial solution as well. And so you can see that the partial solution is connected. But the main difficulty from before is still present. S still has to reach everyone, and it cannot do so with these newly added edges because of this temporal dimension of the edges. So that's bad. We have the general extension, which is NP-complete. The connected one is NP-complete as well. This might push you to think maybe it's a hard problem and the binary partition doesn't work. So that's what we started to study then. So we had the idea to try to reduce to hypergraph dualization first. So I told you before, this is basically enumerating minimal hitting sets, but here I give you a little example of what that actually means. So if you have the universe, or sorry, if you have a set of subsets 1, 2, 2, 3, 4, and 4 and 5, then some minimal hitting sets are 1 and 4 because they hit all of the elements or all of the subsets. 2 and 5 for the same reason. And there's another one which is 1, 3, and 5. It's not a minimum hitting set, but it's still a minimal hitting set. So we use this problem and we reduce it to our problem by basically putting the hypergraph vertices or the elements of the universe as vertices, and then the hyperedges or the subsets as vertices as well, and then we connect them if the elements are in the subsets, and we use some other fancy connections with some very particular times. And the nice thing about this reduction is that we prove that all of the edges, except for these dashed ones, are actually necessary. So that what that means is that there is no spanner or minimal spanner which doesn't have these edges. So all of the edges are actually necessary in all spanners except for these dashed ones. And so that's where the choice is going to happen. And that's basically how we create a one-to-one correspondence between minimal hitting sets and one-to-all-to-one spanners, which is what we need for this reduction. So yeah, that proves that this problem is dual hard. So it's in the gray area. We don't know exactly what that means yet. Nobody has solved it. And then we move on to many-to-all, to the many-to-all connectivity. And we basically have similar results here. So the actual results are basically the same. The reductions are very similar as well. So we have these paths as well, but now it's not a path to allow every vertex to go back to S1. It's basically a path that allows S2 to reach everyone. And the result is also going to be the same because we create such a path 2, 3 from S2 to all the other vertices. And what remains is still this hard problem from the beginning to make S1 connected to everyone else. And this is a very nice result in the sense that it's tight. So we used the minimal number of sources, because if we go lower than 2, then we obtain our tractability result from earlier, the one-to-all case. So this is tight in some sense. And the dual hardness proof is very similar as well. We need to rearrange some stuff, but as you can see from the picture itself, it even looks like the other reduction. So they're very similar. And finally, so this is the last case, the all-to-all connectivity. If we want to enumerate spanners such that everyone remains connected, then we directly thought that this was going to be hard. I don't know why. So this is mainly my colleague from Japan who just has this intuition. And so we set out to prove this. And there's this enumeration sort of reasoning, which at first is very strange because it's an unusual way to prove something. But yeah, let's see. I mean, let's go over how to prove the really negative results. So at first, what you do is you create this sort of auxiliary problem, which we called another all-to-all spanner. And the problem states that when you're given a temporal graph and a set of k all-to-all spanners, you would like to decide if there's another spanner that exists, or if the k ones are all there are. So then what you do is you prove that this new auxiliary problem is NP complete. So we reduced from SAT. Yes, on the left you have the clauses here. On the right you have a copy of the clauses. In the middle you have the variables. And so in a very complicated way, which I will not specify too much, we basically prove that these edges on the left, the sort of skeleton, are all necessary. So all spanners in the original graph, which is this one, are needed. So all these edges are needed in all spanners. And the only edges that we can play with is the zoomed in part in the center, which is here now. These are the only ones which we can play with. And we define the K, the set of K O2L spanners to be the spanners which use this edge and then the corresponding edge on the right. And then another one is this edge and then the corresponding edge on the right. And so these are N individual sort of dummy spanners. And if you find another one, then we basically prove that means you had to solve the set instance. So that's why we obtain NP completeness. And so it's important that we had this K, which is polynomial in the size of the graph. Because afterwards we have step 3, which is we suppose we can actually enumerate all spanners in output polynomial time. And so that means that you can do it in this amount of time. So this is sort of a fine-grained complexity. You see that there's no big O. You have to kind of work with the actual running time. And then you take this running time, this fine-grained running time, and you say that you apply it to this auxiliary problem for some specified time, in which you replace the big N, which was the number of solutions, the size of the output, if you will. You replace it with K, because K is the number of dummy spanners. And so now you have this kind of very nice result, which says that if you find another spanner, another one than the K that you already know exists, then obviously the answer is yes. But here's the kick, the trick. If your algorithm doesn't terminate in this time, I mean, you halt it, but you check to see what's happening in the algorithm. If it didn't terminate on itself, then that means that there must exist another spanner or more than K spanners. So that's the little trick that we use here. And so that means that we can use it to solve another O2L spanner in polynomial time. This is polynomial time, which is a contradiction with point 2, because we proved it NP complete. And so we have that the supposition, which was point 3, is false. There we go. So that was the sort of tricky proof to show that unless P equals NP, O2L spanner enumeration cannot be done in output polynomial time. So here again is this sort of summary of our results. Now you may understand this part of extension and connected extension. We're still working on the journal version in the sense that we're sort of adapting now for other cases. So I talked earlier about this strictly increasing times on your paths. Well, now we're looking at what happens if you allow non-decreasing times as well. So we call this non-strict temporal paths. And we're also adapting it for directed graphs. And we actually have some different results from the ones that we presented here. So we have that the spanner extension for one-to-all, even though it is NP complete for undirected graphs, we obtain that it is actually tractable for directed graphs. And this is basically because in here, you have to make a choice on how to use that edge, whether you use it from left to right or from right to left, or I mean, in one direction or the other. Whereas if the edge is already directed in your directed graph, you don't have to make that choice. And that's basically why it's NP complete here and in polynomial time solvable here. And another difference, but we're still working on this because we think that we might do better just with another reduction maybe. So if we adapt this reduction that we presented in this presentation, then something goes wrong. And if we try to patch it, then we have dual hardness. So we're happy with that. I mean, we're happy with that result, but it's not tight anymore. So I told you here we have K that equals 2 in our reduction, which we're happy with. But here suddenly we need a large K, so a polynomial amount of, a square root amount of sources. So yeah, it suddenly jumps, which is quite funny, but we're still working on that. And then, I mean, another future work which could be interesting, there are many other temporal connectivities, all listed in some kind of nice hierarchy online. And for example, the TC, which they use in this hierarchy, actually corresponds to all that we used here. And they also have 1-all. They don't have these two, I believe, but I mean, they're very natural as well, I find. So yeah, you can there's still some open work or future work which may be interesting. So I have this open problem which I would like to present to you as well. It's regarding spanners. It's not an enumeration anymore, but I think it might be time to add some learning techniques to that. But so this has been an open problem. Maybe I should show it to you. This has been an open problem since my thesis. So this is the first paper we published. So it's 7 years old now. And so we had some nice results in there, but there's still this one open question which remains, which is the following. If I give you a complete graph and then put some times on the edges, can you always delete a lot of the edges so as to just have a very sparse spanner which maintains all-to-all connectivity? And the size would be 2n-3 edges. So the motivation here comes from sort of experiments, but also some results on random Erdős-Rényi graphs, in which this result seemingly pops up out of nowhere. So it has both an experimental motivation, but also a theoretical motivation. But it's still unproved, and there's been some papers on this saying, okay, if we consider some more properties instead of just a complete temporal graph, if we consider that it has this or that, then we actually obtain this, or we obtain a similar result. But this very crucial and very simple question is still unanswered. And so I was thinking maybe it's time to put some machine learning to that, or pattern recognition. But I'm not an expert at all on it. I have had some lessons in this maybe 9 to 10 years ago now. But yeah, so I don't know, maybe an idea could be to... So first of all, there are some polynomial time algorithms that spit out such a spanner, but not for all temporal graphs. Some of them resist. And so I would like to be able to generate a lot of resistant sort of instances. Because if that's possible, then we can look at the actual structure that's been avoiding us for such a long time. But there are some results that say that these are very sparse, in the sense that 99.9 something percent of all spanners after some size, or all clicks after some size, they are solvable with one of the polynomial time algorithms. So to find these, we cannot just use classical algorithms, because it would take too long and there would be too many cases to check. So that's why maybe these learning kind of principles could be handy. So please don't please don't judge me too much when I say learning and I talk about maybe other stuff which is not learning. As I said, I'm not an expert, but so maybe we could produce this sort of very interesting data, the resistant clicks with a gun, where we would first need to produce a lot of data. This can already be done with some generators that exist. And then the gun generator could learn from this data, and it could be verified by the gun verifier. And then someone else also talked to me about answer set programming, so I looked a bit into it. I would need to be able to sort of express my... so this would be for a counterexample. I would need to express a counterexample in some kind of formal logic. And I found out that there is logic for temporal kind of things. So this is mainly used in video games, actually, surprisingly. But yeah, for example, temporal connectivity, so the all-to-all one, can actually be expressed in this linear temporal logic in the following way. So J would be journey or temporal path, and then you would define it with these this formula, and the X here means next. So in some sense, even if you're not able to connect now, Sorry, you might be able to connect in the future. You must be able to connect in the future. Yes, so that's it. I think I went a bit quickly, but this is the first time I talk about this, so sorry for that.
Cool. Thank you so much, Jason. I think Andy's internet connection is acting up, so he asked me to take over this.
I see.
But so, if there's anyone in the audience, feel free to unmute yourself and ask a question, or write it in the chat, and I can read it out loud. I think this was really interesting. The first time I've kind of seen anything about spanners, so looks super cool.
Yeah, it's not the typical temporal graph things you are interested in. I suspect, right?
Oh, but at least it's interesting and always cool to see something new. So I think I had a question, and you actually kind of took it at the end. So I was looking at some of your figures and thinking about your example with like public transportation, the train to Paris, and so on. So
yes.
And exactly those kind of trips are directed, right? So the train leaves from one station at one point in time, and then you kind of said something about, okay, maybe it's easier if, like, computationally it's easier if we also have that kind of restriction. Can you talk a bit about your work about doing this for directed graphs?
Oh, so the enumeration part for directed graphs? Yeah, so let's see. Actually, it's here. So basically, this result does not exist in directed graphs. So in directed graphs, this lemma would say it's polynomial time solvable. And as I tried to say before, that's basically because here you have undirected edges. And if you try to do this reduction, but replacing these undirected edges by directed edges, then you remove the choice from the SAT instance. Because as I tried to explain earlier, if you try to extend your partial solution by selecting this edge, then basically that translates to the SAT instance selecting x1 to be true and x or non x1 to be false, and vice versa if you select this edge instead. Can you see my mouse, by the way? I hope so.
Yes.
Okay, good. Yeah, so if this was a directed edge, then you remove the choice, because if S goes here and okay, maybe it's lucky direction is from left to right, then it can still reach it. But if it chose this one and the direction was from left to right, then it cannot visit or reach this vertex over here. So yeah, there's something well, not strange, but something that removes the choice just by directing your edges. And we were thinking, well, maybe that's fine. Maybe we can still have some kind of nice result, but there's this additional structure that pops up concerning one-to-all. One-to-all spanners, they all have to correspond to an underlying tree, even in the directed case. And so, yeah, that makes it hard, because you cannot, how to say, once you visit the vertex with a tree, then that's done. You cannot come back to that to kind of make it difficult to have a set choice there in some way. This was one of the ways which we found, but that doesn't exist in directed. So yeah, that's basically the difficulty, I think.
Cool. So are there any questions from the audience?
Is there a lot of audience today, because it's a bank holiday in Italy here?
There's 11 people here.
Oh, okay. So they must all be American or English, maybe, or Canadian.
Yeah.
Or at least working there. Yeah.
UK.
Yeah, cool. UK here as well.
So I have another question, if while people get to think about it. So what are some other, like, actually, I have two questions. So first of all, like, what are some other problems that you can kind of solve in this framework, or like other types of problems where temporal spanners are interesting to look at?
Oh, yeah. So temporal spanners are interesting to look at. For example, well, the whole area started with some people stating in some paper that a spanning tree doesn't necessarily exist in temporal graphs, in the sense that you cannot have a sparse structure anymore. You might need a very big structure. And they gave some example with a hypercube in which all the edges were needed to maintain this temporal connectivity. And then some other people said, or rather they continued and they said, okay, but what if you now consider very dense graphs? Is it now possible to delete a lot of edges because you have a lot of choice to delete edges? And some people showed, no, this is not the case. Even in quadratically dense graphs, you can still have quadratically minimal size spanners. And so that's where our work came in with my PhD advisor. We considered the densest graphs, so the complete graphs. And there we actually found that you can actually go down to n log n size, we proved. That has not been improved yet. There has been some adaptations in that work. For example, one really nice result that I like is the people said or proved that there's an n log square n size spanner in which the stretch is logarithmically bounded. So stretch would be the distance is not the original distance in your complete graph is not stretched too much. It's stretched by at most log n. And in our result, the stretch was unbounded. It might have been very, very bad. So yeah, they adapted that. They have this additional log n multiplying factor, but other than that, it's a really nice result.
Nice.
Yeah. So I've done another work as well, in which I was interested in, okay, if I'm now given a class of graphs, can I say what the densest spanner would be in this class of graph? And so yeah, some kind of nice problems like these.
And I guess you could also kind of go down. So one thing is, direction of the edges, right? But maybe you have different edge types in your graph that you want to consider.
Are you starting to think about semantic graphs or?
Yeah.
No?
So I think sometimes it's called, knowledge graphs, or
Yeah.
depends on the domain, right? But at least you know that edges, maybe you have different types of edges, and I guess in spanning maybe you could consider like which types of edges need to kind of be part of your spanner.
Yes. We for this enumeration work, we actually had a little result which is a nice little lemma, but it doesn't really translate into a nice theorem, let's say. But it said that if you have a graph which has directed and undirected edges, then it becomes efficiently enumerable in fixed parameter tractable time. So it's pushing it a little. It's a nice niche result, but as I said, it doesn't translate into a concrete theorem. So we dropped it in the end.
Cool. All right. I think unless there are any other questions from the audience, then I will say thank you so much, Jason, for showing up and
Thank
giving
you for having me.
Yeah, thank you for the great presentation. I just want to mention that, yeah, and thanks for joining for the talk, everyone. So I want to mention that this is the last talk for the semester, and we will be returning with talk probably sometime in June. So we'll be scheduling talks, and we will announce it in the channel and also put it on the website. So please look forward to that. At the meantime, have a great New Year's and have a great summer, everyone. And yeah, thank you so much for presenting, and yeah, thanks for joining.